All right, here is where we left off in the last lecture. We were looking at combinations of capacitors, and we had looked at capacitors that were in parallel. We said those are the easiest ones to think about. So let me jump back here. Capacitors in parallel, capacitors in series. We've done some examples with those. And now we had moved on to a more complicated combination. Now, we had decided that C and 2 are in 2 and 3. C2 and C3 are in parallel. And those are the ones that need to get combined first. We need to do this stepwise. So let's take a look. Now, I flipped the capacitors over because for me, I feel like it's easier to see parallel and series when I'm looking with this rotated view. So that's what I did. Here's a battery, there's a switch. I'm going to close the switch. Ooh, the capacitors are already charged. They're actually not going to be charged until I close the switch. Maybe I closed them and then I opened it back up. But yeah, that would work. So I started with this circuit, and the first step was to take C2 and C3, which are in parallel, and replace that with capacitor 2, 3. Now, C1 was unaffected by that. I only looked at those two capacitors. Those are the only ones that could be combined. And then, once I get to this step, I realize now these capacitors are in series. So I can do a combination of parallel capacitors, and then an additional step of series, and then I'm at C1, 2, 3, and I'm done. I'm down to one capacitor. All right. So that's how these problems work. If you look at the homework, for example, I'm sure there's some examples of this in the homework, you can go back and forth. You can do, some capacitors in parallel, and then check to see if you've got something in series, and then check back and see if you've got it in parallel, and then you have to do a series of calculations at each step. Now, one warning is that the question comes up immediately then, well, can any combination of capacitors connected in any configuration, can we always do these as a series of alternating between parallel and series? And it turns out the answer is no. So there are ways that we could connect capacitors that the parallel series equivalent formulas won't get us through the problem. Okay, so then you either rely on symmetry or you do what are called loop equations. We're not going to do those. So for us, we're going to be able to solve all the examples we look at going back and forth between parallel and series. So now they gave us just a general set of capacitors here. And so I first of all went through and just used algebra. So these were in parallel, 2 and 3. That wasn't so difficult. I could define C2, 3 as C2 plus C3. That was easy enough. But then I got to the series step, and I had to flip everything over. So now, in the series step, I have to do 1 over C1, and then 1 over C2, 3, and that's equal to 1 over C1, 2, 3. Now, it wasn't too terribly difficult. But when I got to this step, I thought, well, I would like a formula where I could write everything in terms of the original C1, C2, C3. So I did that. What I did is I flipped this over. I got a common denominator, and then I flipped this over. And then I took C2, 3, and I put C2 plus C3 back in, and it looked like this. And so for this particular configuration and a different configuration, the formula would work out differently. C1, 2, 3 is C1 times C2 plus C1 times C3 over C1 plus C2 plus C3. And if you're looking at that and saying, well, there's a pattern here, there is, but again, every time I come up with a different pattern of capacitors here, it's going to look different. So these are good to run through algebraically. If we get more than like 3 or 4 capacitors, these formulas can actually get to be fairly complicated. But it's good to try the algebra approach just to see, just to experience how these get more complicated once you add an additional capacitor. So I used this formula. I plugged numbers in. I assumed 10, 20, and 30 again. And for C23, along the way, I got 50 microfarads. And then the overall capacitance I got as 8.33. So there. That's how I did this. Now you could see problems that have more capacitors than this. Okay, and that's, we had talked about before, as that intermediate step. Now, for this example, what I'm going to say is, we got the capacitance calculated. Now what we want to do is we want to go back to the original circuit, find the charge on each of those three capacitors, find the voltage across each of the three capacitors, and calculate how much energy is stored in each. Now, I don't think we've talked about energy yet, so I will just write those formulas down for now. We'll come back and look, because I do feel like when we're analyzing these capacitors, this is kind of the big four. How much capacitance does each capacitor have? What's the charge? What's the voltage? And how much energy is being stored? And we can do that. We can work back and forth. So let's start out. I'm going to say that we have a battery of 60 volts and that we have capacitors that are 10, 20, and 30 microfarads. Now, I built a table, and these tables, I think, are really, really handy to organize the numbers that you're coming up with. Even if you can go through and just do the calculations on your own, if you plug if you write everything into a table, you can cross-check to see if the numbers are all making sense. At some point, if you see an inconsistency in the numbers, you can go back and look for which step that started from. Anyway, so let's do this. So let's see, the voltage is 60 volts. If I look, not at this circuit, but if I go back and look at, you guys remember this one? So I'm going to be referring back to these three different circuits. See the circuit that has C123 in it? It's just got that one capacitor. When I look at C1 and C23, those are in series, and then this was the original circuit. Okay. So, I was given, I circled those numbers, 10, 20, 30 microfarads for the three capacitors. And then the other number I was given is I was told that they were hooked in this configuration to a battery, and I just made up the number 60 because 60 is divisible by everything, and it may give us easy numbers to work with. We'll see. So, because the voltage is going to get divided up in here. So 60 volts, that's what I started out with. Now, I can take that circuit and say Q123 is equal to C123 times V. I know V, and I know C123. So I plugged those together, and I got 500 microcoulombs. So the other item, I guess I should point this out in my table, since I know 10, 20, and 30, I can fill in C23 and C123. So that's kind of the first step, is to get everything in that first row filled in using series and parallel formulas. So the series and parallel formulas will allow me to get everything else calculated in that first row. Once I've got two items in a column, I can calculate the third value. So the way that works is, for example, right here, in the 1, 2, 3 column, I know the capacitance and I know the voltage. I know those two items. I can calculate the missing value, Q123, and that was 500 microcoulombs, and I plugged it in. Now, once you get one of these values solved, that number can get picked up and moved. If you go back and look at the circuits, Q123 is the same value as Q23, and it's the same value as Q1 because they're in series. So I can use this series formula that all the charges match to take that 500 microcoulomb number and copy it over into column 2, 3, and copy it over into column 1. Those are the two capacitor combinations that would have the same charge. And so I did. I copied the 500 into here, and I copied the 500 into here. Well, once I have 500 copied in, now I have these two numbers. I have the C and the Q in column 1, and I have the C and the Q in column 2, 3. So now I can say the voltage is equal to Q over C. Since I know Q1 and C1, I can carry out that calculation. The voltage across capacitor 1 is 50 volts. So that's pretty impressive. Of the 60 volts total, 50 of those volts are across capacitor 1, and it turns out it's related to how low its capacitance is. So a lot of voltage is going to end up across that capacitor. Now when I look at capacitor 2, 3, which is the combination of these together, these two combined have a capacitance of 50. So see how capacitor 2, 3 had 50 microfarads of capacitance. Capacitor 1 only had 10, and that means that the voltage will divide up in a way where the charge on C1 matches the charge on 2, 3. And so that's only at 10 volts. All right, so I got those calculated. Now what we're going to do is we're going to step back one more and say, well, 2, 3 is related to capacitors 2 and capacitor 3, and specifically they're related in a way where their voltages will match. So V2 is going to be the same as V3 is going to be the same as V23. So once I've got that voltage from V23, I can take this number, the 10 volts, and copy it into here and here. So that means I have 2 steps left. I can calculate Q2 and Q3 by using those voltages with the capacitances. I'm going to get Q2 is at 200 microcoulombs, Q3 is at 300 microcoulombs. All right, so if we've done everything correct, so at this point we have the top row completed, and the top row we got because 3 of those values were given, and then I used formulas for series and parallel to fill in the rest. The Q's and the V's, I was given the total voltage, so I'm starting way over here in the last column, and then I worked my way back through these others. So whenever I had a series, I could copy over the Q values. Whenever things were in parallel, I could copy over the voltage values, and then I could solve for Q's and V's as needed. Now, the formula for the energy stored in a capacitor is 1/2 Q times V. And we'll see how we derive that formula. That's going to be an important formula for us. I'm always going to ask about energy stored, as well as the Q's and V's. I just make it a habit to ask about energy stored. And just carrying out those calculations, because we've got all the Q's and V's now, I ended up with that first capacitor, 12.5 millijoules. So it's got a lot of voltage across it, and that capacitor has the most energy stored. It's also got a large amount of, charge, it's got a large amount of voltage, yeah. So it's getting a lot of energy stored there. Capacitors 2 and 3, not as much. So plugging numbers in here, I got 1 millijoule and 1.5 millijoules. When I look at voltages, so I have a total of 60 voltages to work with. If I put my voltmeter here, my table is telling me I will measure 50 volts. So there's 50 volts between point A and point B, and then down here point C. There's only 10 volts here. So I should have 50 volts across capacitor 1, 10 volts here. And going from these 2 points, I can take 2 separate parallel paths. Each path will be the same voltage. So 10 volts either direction. All right. I guess that's it. Oh, I know where that was. So I didn't do the calculation here, but I filled in the energy for C23 and C123. And those actually are a way of kind of checking my numbers also. I thought I had written it down, but I don't see it here. So I just copied them into here. So you can take these, now the first three columns, those are actually real capacitors. Those really exist, C1, C2, and C3. C2, 3, and C1, 2, 3, those are just made up, right? Those are just these equivalent capacitors we're using to represent some capacitor combination. But it turns out their values all follow the same formulas, as if it were an individual real capacitor. And so I can take 1/2 QV. Now 1/2 QV here gave me 2.5 millijoules. And for capacitor 1, 2, 3, 1/2 QV gave me 15 millijoules. And if I've done everything correct, this 15 millijoules should be the combination of 12.5, 1, and 1.5, and it is. So my combined capacitor, 1, 2, 3, will have a stored energy that is the sum of 1, 2, 3. Now, these two individually, capacitor 2 and 3, the same thing should apply. So it should be that the energy I've stored for capacitor 2, 3, which is a made-up capacitor, right, is the sum of capacitors 2 and 3 energy, and the energies match up. So that's a good sign also. The voltages are consistent, the charges are consistent, the energy storage is consistent. Looks good. Looks like we were able to get everything calculated correctly. All right. And you know, if you're on an exam or something and you get stuck and you can look at the table and see that things don't match up, you can always write a note and say, right now I'm looking at this and my voltages don't add up, and so I feel like I've made an error somewhere. I don't know where I've made the error. That works. It lets me know you're thinking along those lines. All right, this is kind of an interesting example. So here they're testing our understanding of what does it mean for a capacitance to have, for a capacitor to have capacitance, and how can I keep track of charge and such. So they're saying this. They're saying, first of all, we're going to take a 24 volt battery. We're going to connect it to those 2 points and charge up capacitor 1 and 2. All right, you guys see those capacitors? Are they in series or parallel? And yes, they are in parallel. They're both going to pick up the same voltage. Now, we're actually not going to combine them though. So this is a different problem. We're not going to combine those 2 capacitors in parallel. But what it does mean for us is each capacitor will now have 24 volts across it. The capacitances are different. They're 2.2 and 1.2 microfarads. What that means is they've given us enough information. We can solve for Q1, we can solve for Q2. So we can calculate those values. Then here's the trick. They're going to disconnect those capacitors and they're going to reconnect them oppositely. So if I just disconnected those capacitors, the voltages would be the same. And so with the same voltage across each capacitor, the charges would just stay there. But if we disconnect them from each other, flip them over and reconnect them, initially it's going to look like this. So now what I have is I've got some amount of positive charge here and some amount of negative charge. Those will cancel out. So we'll be left with some reduced amount of charge on that side. Now, who's bigger, Q1 or Q2? And since C1 is bigger than C2, and they're both getting the same voltage, Q1 will be bigger than Q2. So that says when we combine them in this configuration, these 2 plates, the upper plates in this picture, will both be positive. I don't know what the Q's are yet. We've got to do more calculations. But the 2 Q's up here, here it is, the Q1 and Q2 are going to be the positive sides of the plates. Now, similarly, since Q1 is bigger than Q2, I've got more negative charge here than I do positive, and so the lower side will be, these 2 lower plates will be negative. But what they want us to be able to do then is find out what these little Q1, little Q2s are. So what is it? What are they trying to get us to figure out here? Well, they want us to know how capacitors charge. We can do that. They want us to know that charges are conserved. So there's a way to determine the total amount of charge in the upper part of the circuit and the lower part. And then down here, again, we'll be using charge conservation and voltage matching between the two sides. These charges are going to arrange themselves, Q1 and Q2, such that the voltages will match across the two sides. Once the voltages match, there's no additional force pushing charge through the circuit. So here it is. Here's my 24-volt battery. Here is capacitor 1. Here's capacitor 2. You can see how they've charged. We talked about the capacitors. Let's see. Here's how much charge is on capacitor 1. Here is the charge on capacitor 2. So we've calculated both of these, following all the formulas we've been using. We can see that Q1 is acquiring a larger charge than Q2 because it's got the larger, almost double the capacitance. And what that tells us is that we're going to get cancellation. When we disconnect and flip, see I flipped over capacitor 2 and then reconnected, what's going to happen is the difference between those two charges, which is, I guess we didn't write that down until down here. We're going to flip it over, and now we're going to have different amounts of charge. The positives are going to be on that side, the negatives here. Q1 plus Q2, the combined charges now, is going to be the difference. So again, some of the charges are going to cancel out, and what we're going to be left with, I'm just going to call it Q, and that value is 24 microcoulombs. So now instead of having the 52.8 plus the 28.8, most of that cancels, and we're left with a combined 24. Now, I guess I never added these together. What do they add up? Not that we need to. 70, 80, this is like 81.6, something like that. So of the 80-something microcoulombs of charge that we had, we are now down to 24. Okay, most of the charge canceled out. So the two conditions that have to be met are that Q1 plus Q2 adds up now to 24. The other condition is that the voltage on side 1 matches the voltage on side 2. That's what's going to reach equilibrium for the amount of charge on the two sides. So if the voltages match, that means Q1 over C1 is the same as Q2 over C2. So those are the two equations. See equation 1 and 2? Because we're moving on. Here's equation 1. Here was equation 2. Remember, this is 24 microcoulombs. Hey, I'm back in algebra class. Two equations, two unknowns. How do I solve them? So I took equation 1 and said that boy, I kind of did that quickly in one step. I said this. I didn't write it down. I said that Q2 is equal to C2 over C1 times Q1. That expression right there is the same thing as Q2. I could have done one more step here. I should have. But that is Q2. And so what I've done now is used equation 1, solved for Q2, plugged it into equation 2, and now I have an equation. Everything's in terms of Q1. So I can now multiply this through by C1 and see what I get here, and then pull out the Q1s here. And what I ended up with this formula, the amount of charge that stays with capacitor 1 is the ratio C1 over C1 plus 2 times Q. That's a certain fraction. Now, I could go back and solve for this all over again, but there's an easier way to do that. And that is to say that in this circuit, there was nothing distinguishing capacitor 1 from capacitor 2. in terms of assigning variables, right? Capacitor 1 could have been capacitor 2 and vice versa. And so any formula I've solved for Q1, I should be able to get the formula for Q2 by reversing all the subscripts. So all the 1's become 2's and all the 2's become 1's, and I now have this formula. Now, if I've done this correctly, Q1 and Q2 will add up to the total 24. And looking at these expressions right here, they do. C1 over C1 plus 2 is going to be a certain portion of the total charge. C2 over C1 plus C2 will be the complementary portion of that charge. And so I solved, first of all, for those numbers. It turns out the capacitor 1, it's got more capacitance than capacitor 2, almost double, is going to get 0.647 portion of the total charge, and C2 over C1 plus C2, that's 0.353. So that's how it's going to divide up. And if I add those numbers together, they add up to be 1. Now, to find out how much charge that is, I can take those fractions that we solved, multiply them by the total amount, and that's going to add up to be 24. Capacitor 1, 15.5 microcoulombs, capacitor 2, 8.5. And again, the capacitance on capacitor 1, almost twice as much. And so in terms of charge, almost twice as much charge on capacitor 1. They're both at the same voltage, so it comes down to how much capacitance they have. All right, let's look at some electric energy calculations. That was kind of a fun problem, I hope. Thinking of kind of a puzzle type problem. But let's move on and start looking at how much energy is stored in a capacitor. So it turns out that a charged capacitor stores electric energy. The energy stored is equal to the work done to charge the capacitor. Now, when we talk about work here, what it is the battery is providing energy. The battery is providing energy into the circuit, and when these charges begin building up on the capacitor plates, we're storing energy. We're storing the energy that the battery has provided. The formulas, I'm going to write the formulas down first. We'll come back and see how they're derived. But the formula is 1/2, this is energy, capital U, 1/2 Q times V, where Q is the charge on the capacitor, V is the voltage or electric potential across the capacitor, and 1/2 is 1/2. Now, we know that Q is also equal to C times V, so that's the very same formula with the CV substituted in. And that V is Q over C, so I can also write it this way, and this is a common feature of circuits. When we look at capacitors, we're going to be looking at resistors. It turns out that you can often solve the energies, formulas, often can be solved by 2 or 3 different formulas. So it really depends on what we're given in a problem. If we're given Q and V, this looks great. If we're given C and V, if we're given Q and C, each of these is equivalent to the others. All right, where the heck did that formula come from? And it comes from thinking this way. Now, I don't have the battery in this circuit, but what we're doing is I'm using a battery to pump electrons. Every time an electron gets pumped out of the positive plate and an electron jumps onto the negative plate, and remember, I hope I didn't say this confusingly, I don't have to wait for a charge from the positive plate to go all the way around the circuit because there are electrons right there next to that plate. So when one electron hops off here, one electron hops on. It's hop off, hop on. Just like those tour buses, I guess. Hop off, hop on for the electrons. The electrons themselves aren't moving through the circuit especially fast. Let's see what happens here. So the total charge on the plate comes from adding a bunch of charge together. That's going to give me the total charge. So we can think of the total accumulated charge on my capacitor as arriving in a series of little tiny DQs. DQ, DQ, DQ. Once I add all the DQs together, I'm going to have the total charge. Now, every time we put a DQ on there, there's going to be a little bit of energy. And we're calling that du. Now, this goes back to chapter 23, not too distant in the past. But the amount of energy required to take a little bit of charge and place it on those plates depends on the voltage. If I've got a voltage between the plates, I can use that voltage times that little bit of charge that gets transferred, and that tells me the energy. Now again, these electrons are getting pumped through the battery, so that's energy being provided by the battery. And that's equivalent to what they're calling work. The work done by the battery, the force of pushing on these electrons and displacing them through the battery, that's it. So what I can do now is I can add together all the energy. Every time a little Q jumps on, hop off, energy builds up in the capacitor. And I can add all those energies together. So all the energies, each individual energy is V times dQ. Now at this point, I have a couple of options. I could put V, and the simplest one I think is to put V in terms of Q. So what it says is the voltage between the plates actually starts off at 0. It's not difficult to transfer that first charge. The first charge is easy because there's no charge buildup yet. But transferring the next charge makes this plate more positive and that one more negative, and transferring the next charge, every time I transfer a charge, the voltage goes up, and that means every time I transfer a charge, the energy is a little more, it requires a little more energy than the charge just before it. And this integration is keeping track of that. What it's saying is that this is keeping track of the voltage. So this is the current accumulated charge, and this is each additional charge that's being added. So this is going to be 1 over C. Now when I carry out the integration of Q dQ, that's going to give me 1/2 Q squared. So there it is. The energy required is 1 over C, 1/2. So I move things around. That gave us 1 over 2C Q squared. Now in that earlier list of formulas, we said, okay, once I get 1 written, I can substitute values in and express it differently. So that's the same as 1/2 QV, that's the same as 1/2 CV squared. So when people see this formula, like this one here, there's a 1/2 in there, and back in chapter 23, the 1/2 didn't show up. The energy was just Q times V. And the reason the formula was Q times V is because all the charge was being transferred at the same voltage. But that's not true when we're charging a capacitor. As we just discussed, it's a process where as we transfer more and more charge, the Q keeps changing. When we take that into account, it leaves us with a factor of 1/2. So that's where the 1/2 is coming from. You could plot this. You could say that here is voltage on the vertical axis and here is Q on the horizontal axis. See that first charge that and then the voltage goes up linearly with the charge, just as we said right there. It's the plot of that formula. So the voltage keeps going up. So the first DQ, these widths are all little DQs that are being transferred. The first DQ is not much energy. The next DQ is more, and then more, and then more. We keep transferring a little charge at a time. Each one of those vertical strips in my integration, the area under the curve, shows that each additional DQ stores more energy than the one before it. And so this is another way visually to come up with that 1/2 QV formula. If Q is the distance out to here and V is the final voltage that we ultimately reach on the capacitor, well, that rectangle would be Q times V, but the energy is only half of that. Okay, worth thinking about. We'll see some other examples where we use integration techniques to keep track of energy transfers taking place. So these are useful sort of problems. All right, and then here's a problem in electrical energy storage. It says we have a camera flash. So here's a flash for a camera. There's a flash bulb right here. Ooh, look at all the, well, that's a big capacitor. And then there's other smaller capacitors inside. I don't know if you guys ever remember devices like this. You could actually open up the flash or the camera. But I do know that, it's been a few years back, 20 years ago, cameras that were like this, you could kind of play around with them. You could take the back cover off. You could hit the charge or you would hit something that would say, prepare for flash. And what it would be doing is charging a capacitor. And then you'd hit the flash and the thing would discharge through the light bulb. You could actually open these back and charge a capacitor. And you could stick some conductor in there and see the thing spark as you discharged it, right? So it was kind of fun. I mean, you could take these out, show the kids how capacitors operate. Now, in this camera flash unit, it says we have 150 microfarad capacitor, 200 volts. Oh my gosh, where did they get a 200 volt battery? There's got to be some transformer or something going on here. Anyway, they want to know how much energy is stored. And then what they're going to do is they're going to use the capacitor to store up a bunch of energy, and then they're going to release it quickly. That's the idea of the flash. So the camera's battery can't provide a flash immediately over a short period of time. So instead, you let the battery accumulate a lot of energy stored in a capacitor, and then you release it suddenly through the light bulb. And you get a really bright flash that, again, a battery could not provide in real time. It had to spend a little time charging the capacitor. So here we go. 200 volt battery. I don't think that's in that little camera. 200 volts, 150 microfarads. How much charge are we going to store? 150 microfarads, 200 volts. I got 30,000 microcoulombs of charge, or 30 millicoulombs of charge. Using, my energy formulas, I use the 1/2 QV. There's my 30 millicoulombs at 200 volts. I've got 3 joules of energy stored up in that capacitor, which is a good amount of energy. I've got 3 joules of electric energy stored in the capacitor. Now it says that we can release those 3 joules in 1 millisecond. So when this flashes, it just takes 1 millisecond. So they're asking, what's the average power then? So here's the circuit, here's the capacitor, here's the battery. I got a couple switches. What's the process here? So we close switch 1 and use the battery to charge the capacitor. Maybe that takes some time, right? Capacitor takes a few seconds to charge up. The battery, slowly charges the capacitor. Once we get the capacitor to full charge, which means that we've got the full 200 volts, then we can open up that switch, right? And if the capacitor is a high quality capacitor and it's not leaking charge to the environment, we don't have to flash the charge capacitor right away, or the camera. We can wait. The flash is ready to go. All that energy is in the capacitor. We've disconnected the capacitor. Whenever we're ready to take that picture, when we hit the shutter, the second switch closes. So part of taking the picture closes this switch, and we've got all this charge that can go through the flash bulb. So the power, if this capacitor can discharge through this circuit very, very rapidly, it's claiming that we can come up with 3,000 watts. That's a lot of power. So, and that power is happening because it's a modest amount of energy, but it's being discharged over a really short period of time. All right, so that's an example of storing charge, storing energy, and then having a really high power for a millisecond, for a short period of time. Here are a couple more problems. Conceptual example, although we're going to put some numbers in here and see how, or do some formulas. It says we have a parallel plate capacitor. What happens if the plates have charge Q and then they're disconnected. So if I leave a capacitor connected to a battery, the battery controls the voltage so that the voltage stays the same. But if I disconnect the capacitor, now the battery's not doing anything. Whatever charge has been stored in the capacitor, now it's going to be the charge that is fixed once we have separated it from the battery. So the idea, parallel plate capacitor, it has a certain amount of charge on it, Q, and there's no battery. So the Q is going to stay on there. Now it talks about plate separation. It says in the capacitor, there's a certain gap between the plates. What happens when we play around with the gap? If we increase D or we decrease D, how are things going to change? So let's take a look. Here is my parallel plate capacitor. There's the electric field, there's the plus Q, there's the minus Q, there's the distance between. For purposes of this problem, I got rid of D and started plugging in X because it started to sound like, let's just solve this very generally and ask, if I have a certain amount of charge here and I have a separation of X, and X is a variable, as X varies, what happens to the voltage and what happens to the energy? And so here we go, X is getting bigger, X is getting smaller. So here's what I did. I pulled out the capacitance formula, 1 over 4 pi k, A over distance, took out the distance and I put in X. And I should have not written it in bold. And then here is the energy formula. So if I substitute in the energy formula, there's a factor of C in there. So the energy stored in the capacitor is, if I did the algebra right, it turns into 2 pi k over the area times Q squared times X. Now, I wrote that. I specifically used this energy formula because the Q is constant. We've set this capacitor up so the Q is not going anywhere. It's stuck on those plates. And that means everything inside the parentheses is a constant. So what that's telling us is that the energy stored in the plates, it's proportional to X. So if I have a couple plates and I pull them farther apart, it's got more energy. And if I pull them farther apart, there's more energy. Now remember, these formulas only work if D is much smaller, or X is much smaller than the length across the plates, like the diameter of the plates. So it's not really that we're doing this. It's that we're taking that little tiny distance, that fraction of a millimeter, and bringing it out to 2 fractions of a millimeter. But in any case, in that range, the energy is going up and the voltage is going up. If we look at the E field, is staying roughly constant as long as we keep these things pretty close together. So, oh, here it is. The voltage is 1 over C times Q, and the C, we substitute in the C and look at the X. So as we pull the plates apart, the voltage goes up and the energy goes up. How is that possible? How can I get more energy stored inside there? And where is the energy coming from? And it's coming from us. If we pull the plates apart, that's work. We're transferring, and we got these 2 plates, they're attracting each other, and we're pulling them apart. There's a fixed amount of charge on them, and so we're pulling them apart, we're storing more and more energy as we pull them apart. And so the plot looks something like this. U is a function of X, or U is a function of D. This, I guess, ended up staying D. Here is D1, which is where we started, and here is D2. And the energy is just going to go up linearly. Okay. Now, how much of a force is there pulling these plates together? We now, I think, have looked at formulas like this. We saw this back in Physics 4a, but we saw it recently when we were looking at Chapter 23, that one way to calculate a force is to take a derivative of how the potential energy is changing as a function of distance. So I can take a derivative of the potential energy expression with respect to x, and when I do that, it says that the force is minus 2 pi kq over a. Now again, I'm working in terms of q's because the q's are fixed. And it says that there is an attractive force between the plates, and that force is 2 pi kq over the area. How much work is it going to take? I think they ask about that. So the work required in taking it from x1 to x2, or from d1 to d2, is going to be u2 minus u1. I'm using this formula right here. And then there's all of those constant coefficients, x2 minus x1. So if they give us some distances and some the area of the plates, how much charge is on there, we can calculate how much work it's going to take, and that will show up as extra energy stored in the capacitor. So that's kind of interesting. You're going to have a capacitor that's variable with plate separation. Now, the other example that they give us here, and this one's kind of interesting too, they say this time do the very same thing, except don't disconnect the capacitor from the battery. So, and then they talk about x and 3x and x, and I think what we'll do is the same as before. We'll just solve it once and for all in terms of x, and then we can talk about what's going on. Now, this is going to really complicate things, I think. For myself, I'm thinking, okay, what is going to happen if we're still connected to the battery? Because if we're connected to the battery, this time V is constant. But Q is going to change. Q is not going to be held constant. If I take these plates and begin pulling them apart or pushing them together with the plates still connected to the battery, that battery could pump more charge onto the plates, or it could remove some charge from the plates. Let's see which it is. What's going to happen here? So, same diagram. Here's the, oh, not the same diagram, because this time we're going to close the switch and leave it closed. So it's still going to be connected to the back. This time V is constant. So which formula are we going to use? And I'm going to use U is equal to 1 over 2 CV squared. So notice in this formula, V is fixed. V is not going anywhere. V is not changing. C is going to change. Specifically, well, C is going to change the same as before. The capacitance is going to be 1 over 4 pi k, area over D. And D's been replaced with X. X is our variable. So what that says is when I go in and I solve for this formula right here, U is equal to 1/2 CV squared, I am going to pick up 1/2 times C. So that's going to be 1/2 times 1 over 4 pi k. That gives me 1 over 8 pi k. There's a factor of A, the area. There's 2 factors of V from here. And then that last variable, 1 over x, so I isolated that at the end because everything else is constant. So what that's telling me is that the energy will behave like 1 over x squared. Similarly, I took the Q equation, C times V. The charge is also dropping off like 1 over x squared. So what that's telling us is if the plates are still connected, then the voltage is not changing, and as we pull the plates, or as the plates move away from each other, the charge goes down, and the energy goes down. So I think the plates are going to have a repulsive force on them. Let's try that and see. So here's the graph. Here is U as a function of x. It's a hyperbola. Because it's a 1 over x function. And so if this is the initial separation, x1, I got all the d's switched on this one. This is x1, and then it moves out to x2, then the energies are going to actually drop off. Now, if the energies are going to drop off, that's going to happen on its own. So these plates already are repelling each other. We're going to have a repulsive effect. And it's you know, you might say, well, wait a minute, this is positive, this is negative, why aren't they attracting? But it's a moving target, because what's happening is As it moves closer together, there's more charge, but as you move it farther away, there's less charge. And the overall effect is to create a repulsive force. So I can take du dx, same as before. This time I get 1 over 8 pi k av squared, 1 over x squared. So the force is behaving repulsively, and it's behaving like 1 over x squared. But this is kind of weird. If I get these plates, I have to push them together if they're connected to a battery. I got to push these plates closer and closer, and as I push them closer, I'm storing up more and more energy. If I let go, the plates will push away from each other, okay, if it's connected to a battery. So energy is returning to the battery as the plates separate, as we push them together. More and more energy gets stored in the plates. All right, kind of interesting. This symmetry between constant Q and constant V. All right, there is a, yeah, this is a, this last paragraph is pretty funny. Have you guys ever discharged a capacitor by accident? We mentioned this could be done with a flash camera that you can look for capacitors and see. When I was a little kid, I was the youngest kid in the family, and we had a TV set, and the TV set had a bunch of tubes, and if you took off the back of the TV set, if the TV stopped working, what you would do is you would unplug the TV, you would pull out all the tubes that were in there, you would take them to the drugstore, kind of like CVS. They would have a tube tester machine, and you would test all the tubes, and then they would have cabinets where you could replace a tube that had gone bad. I should have gotten a picture of an electric tube. Electronics used to be, instead of transistors, which are little miniaturized things, there were large glass vacuum tubes that would carry out the same functions. So in our TV, there was a couple of tubes, 1 or 2 tubes, maybe 1, that was down in this special compartment, but inside the compartment was also a capacitor which would get charged, and that capacitor would hold its charge even when the TV set was unplugged. So, there was a message there, a warning, be careful, don't touch the capacitor inside here when you're removing the tube. Well, I was the only one in the family who still had hands small enough that I could reach inside. So, my dad would take the cover off that compartment. He'd go, see that tube right in there? Reach in, really careful, don't touch anything else. It was like playing the game Operation. And I would put my hand in there and grab the tube and pull it back out. And usually it worked, one time it didn't. One time I bumped into the capacitor and got a pretty good shock from that. So anyway, that's, used to be, you had to deal with these things more frequently with our electronics. But yes, capacitors can be dangerous. All right, here's kind of the last topic. Ooh, 2 more topics, right? We're good, we got time here. First of all, we're going to introduce what's called an electric field energy density. And that's the formula right there. That energy density is written in terms of units of joules per cubic meter. And, write those joules in. I wish I would have written the units into this formula. So that would be joules per cubic meter. And the way to calculate the total energy then of an electric field region is to take the energy density and multiply by volume. So this is in joules per cubic meter, this is in cubic meters, and that's going to come out in joules. Now, for a parallel plate capacitor, the electric field is uniform, and that says that if the electric field is a constant value throughout, then the energy is uniformly stored in the capacitor. So the formula for a capacitor, 1/2 QV for the energy stored, the Q value, the charge on the capacitor is related to the electric field by 1 over 4 pi k E times A. The voltage from one side to the other is E times D. If we plug all that stuff together, So here is the charge on the capacitor, here is the voltage, both in terms of electric field. What we get is 1 over 8 pi k EA ED, and if we rearrange things, we get 1 over 8 pi k E squared, which is the formula here, times A times D, and A times D is the volume. Now we haven't derived anything here. What we've actually, well, in a sense, I guess, we've calculated how much energy is stored in a parallel plate capacitor, and it turns out that it's the volume times this expression, and that's the energy density. Now what we've shown is that it works in this case, but we want to look at more complicated situations. We want to look at some situations where the electric field is not uniform. So let's try that. So here we are. What's the potential energy of a charged sphere? We just did an example sort of like this with parallel plates. What we're going to do is, I've got a conductor, let's say, and it's not charged at all. But what I'm going to start doing is I'm going to start bringing in the little dq's. One dq at a time, I'm going to bring it in from infinity. So from infinitely far away, I'll bring a dq in, and it will uniformly spread around the spherical conductor. And then I'll bring another dq in. Now, every time I bring a dq in, that's going to require some energy. It didn't take any energy to bring in the first charge because there was nothing repelling it. But once we accumulate more and more charge, it's going to get harder and harder to bring in those dq's. Now, we can keep track of that in terms of the voltage. So each additional dq adds a du. The du's are going to be given by V times dq, and the voltage is going to go up. The voltage for a spherical conductor, this takes us back to chapter 23, is kq over r. So I'm going to substitute that into the integration, and I'm going to integrate from the time when there was no charge on the capacitor or in the sphere until it's charged with charge q, and then carry out the integration. And what I get is the amount of energy stored on this charge sphere is 1/2 k q squared over r. Now, that's what I'm going to call the construction method. One by one, I'm going to bring in the dq, and I'm going to construct a spherical charge of dq. Let's compare that now. There's a second method we can use to calculate the potential energy. What we can do is, every time we bring charge in, the E field gets built up. The E field due to that charged sphere. We can actually take the electric field, use the energy density method, and come up with a formula for the energy density to keep track of all the energy stored in the electric field due to the charges. So that method we just looked at was keeping track of charge by charge, how much energy does it take to bring the next charge in. But this energy density method is just asking how much electric field have we built up. If we've built up an electric field of kq little r squared, inside there's no electric field if it's a conductor. So we'll keep that simple and just say it's kq r squared outside. Now the energy density formula is 1 over 8 pi k E squared. So inside the integral, that's the energy density. And then we have to ask, well, we have to include all of the different dVs. So we're gonna take the electric field and we're gonna take spherical shells. So we only have to include outside the spherical conductor, but we do have to include all of the, that did not get corrected. Okay, so these limits are wrong, so I guess that's 2 or 3 things that you guys have to change from this chapter. Once a day, I guess, is... Anyway, this should be from big R to infinity. I got this changed, I missed this one. This should be big R to infinity, because the only region we want to include is where there's an electric field. Inside does not need to be included. So again, one more time, big R out to infinity. It gets corrected on this line right here. So the volume elements are going to be 4 pi r squared dr. That's what they show you in calculus when you're learning three-dimensional integrations. Each sphere looks like that. And so when I bring all the factors of r together, I've got factors of r squared from the E field, right? So each factor of E is giving me kq r squared. I brought the kq's outside, I left the r squareds inside, and then I'm getting a factor of r squared dr from just integrating a sphere. So here, a lot of stuff canceled. So factors of k have canceled, factors of pi have canceled, 4 and the 8 have canceled. I'm left with 1/2 k q squared, integrating dr over r squared from r to infinity. 1 over r squared function drops off rapidly enough that I can evaluate this integration. Oh, actually, that's not a problem because we're integrating out to infinity. 1/2 k q squared, 1 over r is the integral from infinity to r. Notice how I flipped the limits to eliminate a minus sign. That's the potential energy. So if I do this as an energy density calculation surrounding the sphere, I get the very same formula as I did when I brought in charges using the construction method. So either approach will work. It turns out they're equivalent. Every time I bring a charge in, the E field goes up, and we can show that the additional amount of E field for every additional charge is a perfectly fine bookkeeping method for finding out how much energy we've stored up in this device. Now, one problem I could just point out here that might be interesting to look at. What if, instead of a perfectly conducting sphere with the charge uniformly around the surface, what if we let the charge uniformly spread through the sphere? Then, in addition to energy stored outside in the E field, there would be E fields inside, and we could go in and carry out a second integration for inside to find out how much energy is stored there. Okay, so something to do in your spare time, maybe. Here's another example of electric energy storage. This is kind of like the flash camera. This time it's a device to charge, right, on the medical TV shows, on ER episodes from 20 years ago. So on ER episodes, they would, patient would show up in the ER and they would say, charge the paddles, and then they would touch the paddles to the patient, and they would build up a lot of energy stored in capacitors, and then use that to discharge it very rapidly to create a large amount of energy quickly. Let's move into dielectrics. Dielectrics are insulating materials, and typically parallel plate capacitors are filled with something. We've gone through the whole chapter up until now, assuming that the capacitors look like this. They're kind of empty, or maybe they have air inside. Well, that doesn't work structurally, and it also doesn't make the capacitor as efficient as it could be. So it turns out by putting an insulating material, and the insulating materials in a capacitor are referred to as dielectrics for whatever reason. So it's a material property. There's a dielectric constant associated with different materials, and it boosts the capacitance by a factor of K. So without the dielectric, we've got a certain amount of capacitance. Again, this is what we've been solving for so far. But if we put a material, insulating material between the plates, which we basically always do, we're going to pick up a factor of K, and we'll get, for the same voltage, we'll be able to store more charge. Now, how does this work? It almost seems too good to be true. But here's what we've been doing all through the chapter. Here's plus Q, here's minus Q, here's the E field between. Anytime we put an insulating material between that, insulating means that it does not conduct electricity. But it does not mean that the material is not affected. So any insulator will polarize. The electrons get pulled in one direction, the nuclei get shifted in the other direction. They don't separate. The electrons don't start moving through the material. But you create a polarization effect, and that offsets the E field. So some portion of the E field is canceled out due to this polarization effect of the dielectric or the insulator. And that means that for the same voltage, additional charges can be brought onto the plates. Additional charges are brought in because the dielectric material polarizes and offsets some of the electric field. And that's what they're saying here. So here are, here's a table. We said that dielectric constants, it's a material property. We can take different materials and determine what their dielectric constant. It looks like we're using capital K here. So a vacuum is defined as 1. That's what we've been working with so far. It doesn't have any effect on the electric field. Air is 1.006, so we've been doing okay, just assuming air is in between. But then you can start putting these different paper, quartz, paper sounds inexpensive, oil, glass. Look, water, that's kind of interesting. Water actually has a dielectric constant of 80. I guess that's pure water that doesn't conduct. I'm not sure how that works. Here's the best one in the table, right? Strontium titanate. You know, let's just jump to that last one. What's this going to do to our capacitance? It's going to be 300 times larger. So that sounds really ideal, right? I build a capacitor, it doesn't have, you know, it's got this, you know, a really small amount of capacitance. We can boost it by 300 by putting the intermediate insulation layer in there out of strontium titanate. So here's a couple of experiments, just thought experiments to think about to close out the chapter. There's a couple of homework problems with these dielectric constants, so take a look at those. But here's a couple of experiments we could think about. Here's a battery, voltage V0. It's been used to charge this capacitor. Now there's no dielectric in this picture. So what would happen if we put a dielectric in? Well, if we put a dielectric in, then we're going to be able to store more charge than we could before. So the capacitance goes up. Capacitance goes up, and we're able to store additional charge on there. And I think, yeah, capacitor is connected to the battery. I see. So in this case, we're connected to the battery, and that means that the battery can provide that extra charge. All right. And so we've got more energy stored here than we have here because the battery provided additional energy for that. Now, what happens if we don't have a battery connected? So we started with the battery connected, but then we disconnected. So in this case, the charge can't go up. And so what's going to happen in this case is that the battery's disconnected. When I put the dielectric material in, so they're imagining somehow this is structurally not changing. I can just slide that material in between and see what happens. Well, in this case, the Q stays the same because it's disconnected, but the voltage will decrease. So when I put the dielectric in, the voltage is going to drop down. So again, the capacitance has gone up because I'm getting the same amount of charge with lower voltage. Now, in this case, if we go back to here, in this case, going from the picture with no dielectric to the dielectric, the charge has gone up. That's storing more energy than before. So this represents more energy than before. And so we're going to have to push the dielectric in, right? And in this case, this is going to be less energy than before. We don't have as much, we have the same amount of charge, but we have less voltage. And so we would have to pull the dielectric out. So the dielectric is going to get pulled into this, between these two plates, we would have to pull that dielectric out. All right, so again, that wraps up chapter 24. The midterm is coming right up. We've got a review lecture, and then we've got the midterm following that. So chapters 21 through 24, stop by office hours, get working through all of the homework problems. I'm hoping everybody's caught up so far, but we have this additional chapter, and we have a practice set of problems too. So look into Canvas and look up the midterm 2 resources, and there are additional problems there for preparation for the upcoming midterm. Hope to see many of you in office hours.